So we are almost done with this unit, and I think I reopened the assignment. So if I didn't, you can remind me so you can review. So for the test, it's going to be the solar system, cosmic collision, and what else? Oh, and the first unit of this, 7.12. Okay, so we talked about the size of stars, and as I told you, when the stars are on the main sequence, their luminosity, so the power output, how much energy is going to be burned per unit second, depends mostly on the temperature to the fourth power. So typical question, if you multiply the temperature by 10, the luminosity, the metabolism will be multiplied by 10,000. And the size, of course, matters a little bit. It's going to change a little bit, but not that much. Most of the dependence will be on the temperature. Okay? But when the stars run out of hydrogen, they're going to be swollen right before they get to burn helium. That will be the next phase. So in that case, okay, so for example, our sun will be swollen, will increase in size as a red giant. So the temperature of the sun is going to decrease because red will be cooler than white. However, so it will be a cooler temperature. However, its luminosity, so you see here you have the luminosity, will be larger than the sun, even larger than blue stars, even though this is not possible when they are on the main sequence. So when they are on the main sequence, a red star, okay, will be cooler and less luminous than a white star, and a white star will be less luminous than a blue star. So that's only true when they are burning their fuel, hydrogen into helium. When they're going to run out of hydrogen and they go to burning helium, they will become red giant. So if they are blue star, they can become also super red giant. So in that case, even though they're going to be cool because they're going to be red, their luminosity can be larger than blue stars. Why? Because of the size. So even though they don't burn their fuel very quickly, because they're going to be so large that they can outpower blue star because of the size. Is that clear? So if we want to do a little bit of math, but not that much, you see, the energy output is proportional to the output per unit second, so the oomph, how fast the fuel is burned, depends on the temperature to the fourth power. So that will be the dominant factor when the stars form the main sequence. But when they leave the main sequence, we can take this in account. So that will be the surface area of the stars. That here, it's called the Boltzmann law. And we already talked about that. If you find the area under that curve, you're going to find the energy per unit second per unit area. So that's Boltzmann law. But now you multiply by the size. Okay? So that will be the energy output per unit second per unit area. Well, which is a very convenient, very simple, only algebra based, not even algebra 2, just algebra 1 equation. Because you see that if you know the temperature of a star, because you know its class, spectral class, and you can find its luminosity, so its oomph, then you can find the size. So we have all those informations about stars. So again, as long as it's on the main sequence, a cool star will always give out less energy than a hot star, except when they are at the end of their life and they become giant or super giant. So in that case, they can outpower blue star. Okay, so that will be the case of Betelgeuse, for example. So Betelgeuse here, part of Orion, is a super red giant. So it used to be a blue star, then it got swollen out, and at some point it's going to end as a supernova type 2. Maybe it will be a black hole left behind, but you see, it's very cool. Okay, temperature is low. However, it's so big that it will outpower a blue star like Rigel, which is blue. So, for example, if you say that the temperature of Betelgeuse is about, it's even cooler than the sun, okay, because the size is multiplied by 1,000, the oomph would be multiplied by 1,000,000 because the size grows as the radius squared. So we have a perfect world for ourselves because you don't want Betelgeuse as a sun. It will be too hot, and plus it will go up to Saturn. Right? Although we don't know what's going to happen in a million years or 500,000 years from now, because the sun is going to increase the rate of fusion, so it's going to be very hot, so the ocean are supposed to steam away, but it's fine, we won't be around. Okay, so size matters. So for example, here you have lava from a volcano. And the lava, if you take a little bit of lava, it's not that hot. It's like burning like a candle, okay, as hot as a candle. But of course, if you increase the surface area, it's a compounding, so it's gonna you're gonna get a huge amount of luminosity, so much that someone has to wear like a special suit and protect the eyes. It's not that it's hot, but it's a lot of that. Okay, so that's the idea of a star, of the size, sorry. So for example, if you take manure, I don't know why they put manure on New York City. I don't know why New York City. But anyway, manure is very hot, but it won't burn yourself. But if you take a lot of it, it's gonna be super hot. So here, imagine you have a star looking like a disco ball. Disco ball. That's maybe you don't know what it is. That's my time, and that was in the 80s. And you divide that sphere in small little square. Even if the little square here doesn't output a lot of energy because the temperature is low. Okay, if you have many of those little squares, then it's going to output a lot of luminosity. So size matters when the stars leave the main sequence. So that's the idea. So again, you have Betelgeuse here, even though it's cool because it's red. Remember, red is cooler than blue. It can outpower a blue star because of its huge star size. So it's a red supergiant. So just I thought that is cool because it's like a model. Like you can see the difference between Betelgeuse, which is very cool because it's red, and Rigel, which is blue but small. So Betelgeuse can outpower Rigel. That's the idea. So those stars, they can inflate to a humongous size, right? Even though they are category M, which means very cool. So, oh boy, a fine girl kiss me, lovingly, me, so it's red. Okay, Antares, same thing, it's a red giant here. Okay, it's a M star, so cool. Temperature is only like that much, 6,000 Fahrenheit. So it's cooler than our sun, which is 10,000 Fahrenheit. And then you have monster among stars. Okay, they are really monsters. So this one was discovered in 2010. So you can see relative to our sun, which is very average, nothing special about our sun, except that thanks to him we have life, of course. Our sun is called a yellow dwarf. Okay, it's very average. It's really at the center of the main sequence. Not too hot, not too cool, perfect. And compared to the sun, you see they have those huge monsters here. Okay, you can even compare the size here. So you have the Earth, which is the size 100 times smaller than the sun, and you have this monster. So that monster is so big that it's gonna burn its fuel so fast. And the color, of course, is blue because big, when it's on the main sequence, means that gravity is trying to squeeze the star. So it's going to increase the metabolism. So as a consequence, it will have a very short life. And even though we can see it from Earth, it's already dead. Its life is about 10,000 years. So that's super, very young. So it's really living out and dying young, 10,000 years, like it's infancy for a star. But because the star is so far away, 100,000 light years away, so it takes 100 years for us to detect it. It's already dead, but we don't see it yet. We have to wait, right? So we are looking in the past, but it's already gone. So it was found in the Large Magellanic Cloud. So this is the Milky Way, and we have two satellites, two small. They don't call it small; they call it dwarf. I don't know why they like dwarf so much, like dwarf planet, dwarf galaxies. So dwarf galaxies orbiting our own galaxy, and that's where it was found. Okay. Okay, and size can be small. So you can have the opposite. You can have something small, okay, hot but small. Because it's small, it won't give out as much power. So if you look at the HR diagram, you have white dwarf here. Okay, so their temperature can be very large because what's a white dwarf? It's a dead corpse. It's dead. There is no more fusion, and it's an exposed core. So our sun, after this stage here, so here it will be a red giant. It's going to burn out its outermost layer. Then the core will be exposed and it's dead. There is no more fusion. When you say that a star is dead, it means it doesn't burn fuel anymore. It will become a white dwarf. So the temperature is very high because it's the core, but so it will cool down step by step. But you see, it's not as luminous as the sun or even those stars here. Why? Because of the size. It's so small. Make sense? So don't be scared, okay? If you still have people who are scared. I'm not sick. I have terrible allergy. I'm waiting for the rain to get better. Okay, so white dwarf. Okay, so this sun here will become a white dwarf, and you see it will be about the size of the Earth, but huge mass, squeeze to a small size. Okay, so if it's 100 times smaller, 100 times 100 is 10,000, so it's going to be 10,000 times less luminous, for example, than our sun if it has about the same temperature. Famous example will be the companion. So we're going to see that stars, they don't like to be single. They like to have a companion or two companions, ménage à two or ménage à trois, ménage à deux or ménage à trois, but not too much. Right after it becomes unstable. So ideally, that will be a ménage à deux or ménage à trois. So that's Sirius. Here is the brightest star in the sky. You already know that. It's a dog star, and it has a companion, and the companion is a white dwarf. So it's not very luminous. And sorry for the sniffing. Okay, so we get something very important, and these are called variable stars. So at the end of their life, some stars, not all of them, some stars start to inflate. And then not only that, but they're gonna blink. So they go bright, dim, bright, dim, bright, dim, right? So and they're gonna have a period. So the period is the time it takes for one cycle to go bright, blink, bright, dim, and bright. And okay, let me show you on the HR diagram. So some stars at the end of their life will be like this, right? So it will go bright, dim, bright, dim. So the most important, the one that we're gonna talk about today, are called cepheid variable. Okay, we're gonna see why it's called cepheid. So cepheid variable, and you have another group here. And the most famous one is called Mira, because this star, Mira, was the first variable star ever detected. So it happens at the end of their life. Not all stars will have this behavior. They go bright, dim, bright, dim, bright, dim. Okay. You too. You have allergy, right? It's because when it doesn't rain here for a while, you have so much dust. There's too much dust. So bad, isn't it? Yeah, me too. It's something outside. Like my nose, like it's terrible. We need the rain. If you don't get rain here, we have so much pollution and dust. So anyway, okay, Mira, and that was one of the first variable star ever detected, and it's part of Cetus. So Cetus is like a whale, and Cetus is a monster. Remember the story that was supposed to eat Andromeda? Because the mom of Andromeda was the vain queen Cassiopeia, and she offended Neptune by saying she was more beautiful than the nymph, I think, of Neptune, with kind of his daughters. So he got upset. So he said, okay, to the king, you have to sacrifice your daughter Andromeda to Cetus the monster. And then Perseus comes and save Andromeda. Apparently, Hercules also was supposed to kill that monster. So I don't know who killed it. Is it Perseus or Hercules or whatever? Or maybe he reincarnates each time. I don't know. But that's the story. So Mira is over there. And it goes from magnitude from 5 to 9. And remember, 5, 6, 7, 8, 9. So that means the brightness is multiplied by 2.5 times 2.5 times 2.5 times 2.5. Okay, so I don't know. I think I have found like a YouTube video.
Mira, designation Omicron Ceti, is a binary star system in the constellation Cetus. It consists of a cool, pulsating giant, the famous star Mira A, and a low-mass companion, Mira B, which is a creamy matter that has been shed by its larger part. It is the only known star with a cog-like tail. Mira is racing through space faster than a speeding bullet. It moves at 130 kilometers per second relative to the galaxy, and, as a result of its large space velocity, it has heated and compressed the gas in its path. The heated gas excites the molecules of hydrogen and heavier elements pouring from the star, causing it to glow in the ultraviolet band. It is pulsating variable whose brightness ranges from 2.0 to 10.1 over a period of 31.966 days. Surface rises and falls. Visible to the naked eye at its brightest, Mira can be seen only with optical aid for most of its cycle. It is the prototype and brightest long-period variable, or Mira variable, and was given its name, meaning wonderful. Thank you. Mira, designation Omicron.
So it's interesting because you see that stars are moving, okay? They are not static. So this one moves really fast and it leaves like a tail behind it. In addition to that, that star gave the name of a group of stars that are variable as well here. So it goes bright, dim, bright. And now we're going to talk about the cepheid variable. Cepheid variables are very important because they use those stars as standard candle. So it means, thanks to Henrietta Leavitt, so we're going to talk about Henrietta Leavitt. She's part of the computers, from Harvard, the Harvard group with this guy Pickering, Mr. Pickering, and he had a group of women working for him, going through all those photographic plates, and you have Annie Jump Cannon, but you also have Henrietta Leavitt. We talked about her, and she discovered that cepheid variable not only are variable stars, so they go bright, dim, bright, but also that the period of those blinkings are related to their luminosity. So it means if you see a cepheid variable and you compute the period, okay, so how long does it take for one cycle to go bright, dim, bright? So you compute the time for the cycle, you can find the luminosity. So it means the oomph, okay, the energy output. And once you have the luminosity of the star and you compare to the brightness, you can find the distance. So it's like a cosmic tape, like a cosmic ruler, right? It's a way to measure distance. So we already talked about that. If you have a light, okay, like this one, okay, my phone here, it has, I could find, the luminosity, the watt. And of course, if you are far away, Woody, okay, he's not going to see that light as bright as I see it. And if he give me the information how bright it appears to be, and I compare to this one, I can find the distance. I don't see well far away, so I'm not sure about the name. You tell me after. I'm not only I have bad allergy, but I'm partially blind. So anyway, so these are the cepheid variables. Okay, so they were discovered here in the 18th century. And so why are they called cepheid? Because they were found in the constellation Cepheus, and Cepheus means the king. And which king we are talking about? We're talking about that king, the dad of Andromeda, who was sacrificed to the monster. So the king and the queen was Cassiopeia. So anyway, that's just for the story. And so the first one, because those cepheid variable were found in that constellation, so they were after that they called cepheid. They were called the cepheid variable. So this one, delta cepheid, is one of the very famous cepheid variable. And I have found a website. Maybe I will post it. But you can see here is Cassiopeia, that's the vain queen. And this is Cepheus here, so that will be the king. And here is the first cepheid variable discovered. So it's hard to see from here, from Miami, but you can see it late fall, beginning of the winter. So you see here Cassiopeia, the queen. This is the king, and that will be the delta Cepheid. So the first cepheid variable, and again, it's a variable star, but a special kind of variable star. And it goes bright, dim, bright. Cassiopeia, this is Polaris, the North Star. So very, very important. So because because you can use that to find the distance, cosmic distances. And that was discovered by Henrietta Leavitt. We don't have many pictures of her, but here she is. And it's lucky for her that she found a job, because she had a disease, and then she was deaf, and she also died young. So these cepheid variables are used to measure distances in the universe, and it was used by Edwin Hubble himself to understand that Andromeda galaxy, okay, is not a nebula, it's a galaxy far away from us. And then he used the cepheid variables to find the expansion of the universe. So cepheid variables are very important. And you can see here that luminosity. So here you have the magnitude, okay? And it goes decrease, increase, decrease, increase. So what's the big deal about them? It turns out that, and that's Henrietta Leavitt here, cepheid variable, another example will be Polaris, one of the stars here, the companion of the North Star. So she discovered cepheid variables in the Magellanic Clouds, right? And at the time they knew the distance, and she's the one who discovered that there is a relationship between the oomph, the intrinsic oomph of the star, so luminosity, and its period. So you find the period, you find the metabolism of the star, so the power output, you compare to the brightness, and you can get that to find the distance. So it was a big breakthrough. So I have a very nice movie that will tell you the story. Oh, let's see. So this is Henrietta Leavitt. I think this is a movie. They did a movie, but you see, at the time you had to use photographic plates to analyze them. Well, I think they have only one picture of her, but this is a very nice movie. Oh, yeah.
We see the night sky as a vast array of thousands of luminous objects that appear as tiny dots. Among them, there are several nebulous patches called galaxies. How far away are these galaxies? Are these objects scattered in the stars just as small as they appear to the naked eye? Or are they larger? How far away from us are they? And how can we tell? The answers to these questions came with a crucial discovery, but it was not made by scientists or scientists, but by a modest, hard-working astronomer, the remarkable Miss Henrietta Leavitt.
I was working at Harvard College Observatory as one of many computers, working for minimum wage and sorting through piles of data, thousands and thousands of stars. For centuries, sailors from the southern hemisphere spoke of two fuzzy patches in the sky that looked like detached parts of the Milky Way. These became known as the small and large Magellanic Clouds. They could not be seen from the northern hemisphere, but we had many good photographs of the clouds taken from our observatory in Peru. I spent many years measuring and studying the stars in a small Magellanic Cloud. I soon discovered that the brightness of many of these stars changed periodically. When a star was brighter, its image on the photographic plate looked bigger. When it faded, it looked smaller. These are called variables. Day after day, month after month, year after year, I searched for those variables, measuring their brightness and computing their periods. And then, a pattern started to emerge. I noticed a remarkable relation between the brightness of some of these variables and their periods. The brighter variables had longer periods. The fainter variables had shorter ones. The relationship was unmistakable. I was able to do precise measurements for 53 such stars. Then I made a graph. On one axis, I plotted the length of their periods, and on the other, the maximum brightness. A precise mathematical fit emerged, showing what became known as the period-luminosity relation, the laws obeyed by these stars. These stars became known as cepheid variables, or cephids for short, as we first found them in the constellation Cepheid.
That's a king.
Relationships like this don't happen by accident. Rather, they must reflect something deep about the true nature of these stars. I hope that systematic studies of these variables would shed more light on this issue, but I had no time for that. Others would have to take on that task.
Indeed, they did. Henrietta might have continued to learn, had she not been held back by an poor health. She died several years later after battling long illness. But the results of her labor lived on. Astronomers quickly realized the importance of Henrietta's discovery. Cepheid variables are easy to spot, and they have been found all over the sky. A&R Bellsprung realized that they could be used as light beacons to measure distances.
So the HR diagram author
was able to estimate the distance, small measurable power. Harlow Shapley used Henrietta's period-luminosity relation to estimate the size of our galaxy. And Edwin Hubble used this relation to measure how far away other galaxies are from us. He found that the universe is expanding. Wendy Friedman led a team of astronomers that found out just how quickly it is expanding. Using Henrietta's period-luminosity law, they were able to measure distances to galaxies that are some 66 million light years away.
So the computers.
Henrietta's discovery became one of the foundations of modern cosmology.
Miss Leavitt had the happy faculty of appreciating all that was worthy and lovable in others, and was the
So that movie was done by Harvard, I think. But you can imagine the work done. Okay, it was a very tedious work because you have to look like again and again and again all those photographic plates for a minimum wage. But they were very passionate, I guess. Okay, so it's going to be very important, cepheid variable, to measure the distance. So we can say, okay, at that distance, I'm going to see a cepheid variable. So I can find the distance by comparing the brightness and the luminosity. And once I have the distance and I have the speed, the redshift of those galaxies, so then I can prove that the universe is expanding. And later on, instead of using cepheid variable, are going to work up to inside our galaxy and beyond our galaxy, but at some point it's too far away. We cannot use them anymore. So that's why now they are using for very, very far away galaxy. They are using what is called supernova type 1A. So huge explosion. And we know the luminosity of supernova type 1. We can compare to the brightness and we find the distance. And that's how they discovered that back then the universe was expanding, but not as fast as today. So the universe is accelerating. So, but same idea of standard candles. Okay, that's now they do it with computers, right? And a graduate student paid minimum wage to check. But back then you had to do it with your eyes. Okay, so I think this is the last subunit. So this is not on the test. So test number 3. Okay, Monday. Don't forget. Don't come to class. I will open it from 10 to 12. I will post again because I'm sure I'm going to have students who are going to miss it. So anyway, again, the mass the mass of stars really will define all the intrinsic properties of stars, right? Okay, so for example, the size depends on the mass. It's about proportional. And anything else also depends on the mass. Like luminosity depends on the mass of the fourth power. Life also depends on the mass. Remember for test number 3, if you multiply the luminosity by 10, life will be divided by 10. And anything else also depends on the mass, except, of course, distance. So how do we know? How do we find the masses of stars? We have to use binary star systems. Okay, so most of stars don't like to be single. They're in binary system or 3 stars, maybe 4 stars, and then it becomes very unstable. So here you have an example of a binary system. So 2 stars. And what happened with them is that when you have 2 stars like this, they're going to have a center of mass somewhere. So that will be the center of mass. And both stars are going to orbit their center of mass. Right? So how close on the center of mass depends on the mass. So this star will be closer, and this one will be further away. Okay, so for example, here, if you have 2 stars and they have the same mass, that will be the center of mass. If you have a small star and a bigger star here, like I have here, see the center of mass will be closer to the big one. If you have like the sun here and Jupiter, the center of mass can be inside the sun because it's so big. But nevertheless, the sun will still wobble. It will be wobbling around its center of mass because of Jupiter. And that's how we can detect exoplanets, even though you cannot see them. But if you see a star wobbling, that means something is tugging on it. And that's how you can detect other planets. It says video binary. So let's see if I have a video. Here maybe. You see? So what's interesting is that you can put like a stick, invisible stick, between them, and it will go through the center of mass. So the center of mass is close to the big one, further away from the close one. So it's like a seesaw, right? If you play seesaw with someone, like when I was playing seesaw with my kids, for example, I will sit very close to the fulcrum and they will sit further away. Otherwise, it's no fun. So it's like, so the equation is very simple. M1R1 equals M2R2. So if you are 300 pounds and your kid is 100 pounds, so it's a ratio of 3, you want to sit 3 times farther away from the axis of rotation. So that's one equation that you have with the mass. The second equation, you have momentum. So it means it's Newton's third law. So this one is tugging on that one, so that one is tugging back. For every action, you have an opposite and equal reaction. So it means I'm going to tug on you, and this one saying I'm going to tug back on you. So the tug is the same, but not the consequence, because of course this one is very big, so it's not going to go as fast. This one is smaller, so it's going to go faster. But for every action, there is an equal and opposite reaction. So that will be conservation of momentum. So if you are doing physics, maybe remember from high school, M1V1 equals M2V2. You cannot tug without being tugged, and you cannot tug harder than you are tugging. Okay? In addition to that, so that 2 equations, in addition to that, you also have the equation from Kepler, third law, that was fixed by Newton. that gives you a relationship between the time it takes to go around the center of mass and the distance to the center of mass. I think he called that the harmony law, Kepler's third law, and then it was explained by Newton using universal law of gravitation. Okay, see? So that's how they found the mass of stars and how they found the relationship between the mass, the luminosity, the mass, the size, the mass, the life. Everything about stars depends on the mass. And all those relationships were discovered because they were able to find the masses of stars. Make sense? Any question? Okay. So that's my seesaw. You see, if someone big here has to be closer to the fulcrum. So M2 R2 equals M1 R1. You can apply same idea to a star. And also conservation of momentum. I tug you, you're gonna tug me. But of course, this one is not going to move fast as a consequence of the tug because it has more inertia. Okay, and so if that star is very big, you see the center of mass will be inside, like the sun and the planet, for example, or the Earth and the moon. Earth and the moon, same thing, the moon and the Earth, and the center of mass will be inside the Earth also, but still the Earth is wobbling because of the moon. And that will produce the tides. So all those relationships here, with this relationship here, remember, there is a nice relationship from Kepler's, so you can use that. That's Kepler's third law, and you can use that to find the masses of stars. That's how they did it. Okay, and once they have the mass of stars, they find all the relationships we talked about, which are summarized here. If you have the mass, temperature, everything depends on the mass, but the distance, of course. Okay, so this, you have the real binary stars, and then you have fake binary stars, meaning as seen from the Earth, okay, you have those two stars, and you might think they are close to each other. That's because we don't have the perspective. So they are not close to each other. It's just what it looks on the sky. They're gonna be glue on the celestial sphere, but they are fake. That means they don't orbit each other, the center of mass. So they are called optical binaries in that case. So this one is very famous because at the time when we didn't have the optician that we have today, to check your eyes, no problem. They will use nature to check your eyesight, if you were good for the army or not, for example, because they didn't have glasses at the time, I guess. So they will ask you to look at the sky and say, okay, can you tell them apart? Yes or no? For me, it will be a disaster, right? So that was used as eyesight, but they are fake. So that's the big deeper here. So fake binary. And then you have, it's called optical binary. And then you have visual binary. So that means you have two stars, okay? They orbit their center of mass, but you can see it with a telescope, for example. Okay? So that's why it's called visual binary. And you see over the years the position around their center of mass. So you have optical, fake, visual, real, but you can see it. Okay? So here are some examples. In the constellation Cygnus, you have two yellow dwarfs And in 1996, oh yeah, that's where they found the first exoplanet around like a star, not a pulsar. So the first exoplanet that they found were around a pulsar. 1995, but 1996 they found the first exoplanet around the main sequence star, and that was found here in that constellation Cygnus. Okay. Okay, this is another example. I don't know. Oh, let's see here. That's also a nice one. You see when the star here is really big, or you have a star on the planet, it's still orbiting its center of mass, but the center of mass is inside. I'm going to stop here because my nose is